our next speaker is Chen Kleissl. I think Chen is here. Hi, good to see you. You want to share your screen? Okay, brilliant. So Chen received his PhD from Johns Hopkins University, and he is currently a professor in the Department of Mechanical and Aerospace Engineering in UCSD. And he's also the director of two centers. One is the UCSD Center for Energy Research, and the other one is the DERConnect NSF Research Facility Center. I think that will connect to what he will be talking about today. So he will talk about interconnected distributed energy resources, which is a topic I found very interesting. Okay, so without further ado, so Chen, let's welcome Chen. Thank you.
Thank you, Minghua. So the purpose of my talk today is to advertise this facility to you. We're currently constructing it, but we'll be ready in about 2 years to welcome customers, hopefully some of you, to actually use the facility. I also shared the slides in the chat, so if you want to go back to the slides or move forward, if it's too slow or too fast, you can use that to your advantage there. Here's our team. We have many professors from UCSD in controls and social science and others, and several staff members who work on constructing the test bed. Some motivation here. So in California, we of course are one of the most progressive states in terms of renewables. And just in April this year, we hit actually 98% of share of electricity coming from renewables. This is the whole day shown here. And the green line is the renewable production in megawatt here. And you see that in the afternoon, actually, we hit 98%, so much higher than gas and hydro and batteries. And we are able to export energy to our neighbors. This actually, aside from the number, this looks quite good because it's actually quite smooth of a curve. So we have in the nighttime wind power production, daytime we have solar power production added, and then going back to wind power. But it's a fairly smooth curve, so that's good news. And of course, there are some challenges here that remain, and that is on some days we will likely see much larger changes in the production. So we did some analysis in the San Diego region where we see here satellite images. This is the coastline, and these circles are solar power systems. And you see from 8 o'clock to 8:30 to 9 o'clock, the clouds retreat, and then the color changes, which means that we have more solar power production, as we can see in this graph here. So that means that on some days, we probably will see larger ramps or changes in production. And that brings us to the challenge of how can we mitigate those changes. And here we have several paradigms of how we use load flexibility to address renewable variability. And this, based on the time scale, these are called shape, shift, shed, or shimmy, based on a paper by Lawrence Berkeley National Lab. So example here is for shifting, which means you shift energy on time scales of hours to days. An example here is the California Carbon Intensity Index. So we see on some days now actually have 0 carbon intensity in California at midday. We have the highest carbon intensity in the evening. So how can we shift energy usage from evening to midday? Or shedding load, which means that you try to reduce load in the peak hours of the year, like it's shown here for Rhode Island. And then shimmy means that you try to shift load on very small time scales where you, for example, you address frequency regulation challenges. So with that background, we now have learned that there will be large fluctuations in renewables in the future, and this will be significant when we have a high penetration of renewables on the system. And that will lead to two things. One is curtailment of renewables. The other is more expensive electric rates. And the most economical solution to that really is flexible load and changes in those loads. Right now, it's still difficult, but in the future, we will have millions of these DERs, distributed energy resources, that are connected to the grid, and that could be operated remotely to participate in the load flexibility, such as energy storage, electric vehicles, HVAC, and lighting. And in that way, we can try to have real-time and scalable control, meaning control that can be implemented for millions of devices. That's where this testbed comes in. So this testbed is a testbed that tries to emulate the entire grid and allows people to test these controls methods for a very large number of devices. So this testbed will have 2,500 actual devices and up to 2 million simulated nodes. We will use small form factor DERs, meaning DERs at low power, like one light fixture or one plug load, one battery. It's a national testbed, so anybody in the country can use it, and there's also ways to use it if you're international. And it's possible because we have developed a number of advances at UCSD in the past 10 years. One is integration of renewables. We have also upgraded buildings to be more operable. And we have lots of electric vehicles on campus and use those as a load flexibility source. So here you see that vision of the future grid, where we have still some centralized generation, but also now more and more localized generation. And we now try to balance local loads as well as respond to a central signal. You can do that in multiple architectures, like you see up here. So you can group these DERs together in smaller groups and then have aggregators, or you can have even more chaotic architectures where all the DERs just talk to each other and try to follow the load signal. From a mathematical standpoint, we're trying to follow this cost function. So we want to minimize a cost function that's subject to constraints. So we want to maintain, say, a certain load locally, but still meet the overall constraint here. That is the overview of my talk. So I will present to you the testbed overview and then go over some technical elements of the testbed later. Just one note on what DERConnect is not. It's not actually a large investment into physical infrastructure. But we're not buying large batteries. We're not buying large solar power plants. We're mostly connecting these existing systems and try to make them more accessible and controllable. It's also testbed not for individual DERs. So there's other testbeds where you can test the battery or you can test the electric vehicle. Here we're looking at thousands to millions of DERs being tested together. So here's the overview of the testbed. So on the right-hand side, you see maybe the more standard type of DER connectivity, where we have 11 buildings. We have a couple hundred electric vehicles. We have some solar power plants with smart inverters on them. We have energy storage testbeds. Those will all be connected to our database and control system. And then we have a separate facility that's more of a lab facility, which we call the core. And in that facility, we have access to also simulation capabilities, which is a real-time simulator for simulating larger grids. We also have a connection to other devices through a plug-and-play hub. We have an islanding controller, so we can island this facility to do more advanced tests. And then we have emulators, which means we have batteries and inverters, and those can emulate any remote device like a wind turbine or a power grid element. So we can make it look like it exists locally. Then the key other users, we want to make this user-friendly, so anybody from the outside can log in and control these DERs. So here's an example of a control layer. So we have the individual DERs at the bottom here. So one electric vehicle or one solar power plant. And then we connect it to an agent. So the agent is the smart computing system that's just dedicated to a single DER. So it's, in a way, its combined usage is one node of this testbed. And then we have data layers. Those data layers connect all the data from all of the systems. And the control layer then allows us to flexibly control the connection of these devices. So in one control layer, for example, this agent could communicate with only that agent. In the other control example, this agent could communicate with all of the other agents in a certain layer. Then all that goes to an admin, and then here we can log in as a remote user and utilize this testbed. Timeline, so it's still not ready to be used. So we're right now about here. So we are building the individual DERs and connecting them to our system. Then we'll have next year a simulation testbed operational. And then we hope that by the end of 2024, we'll be open for beta testing of the testbed. Then the official start date is in the fall of 2025. So a little bit of discussion on the user experience. So this is a unique testbed because it focuses on distributed controls. So we have built in the ability to test distributed controls methods. It's very versatile. So we can do many other tests also, like cybersecurity tests or building operation tests or large battery tests. We can attach simulation and HL environments to this, so we can scale it up to large grids. And it's a living lab here, so we have actually real buildings, real electric vehicles. So it's a way to test how these control methods will function in reality, where we have to often compromise between comfort and energy issues. It should also be convenient to be used. So we have low-cost tests, so starting at $5,000, and then of course, if you want to be more complicated, will be more expensive. It's easy remote access, so you can log in from your location. We don't have say firewalls that will prevent others from outside to use it. And it should be plug and play. So we have open source software, so you can basically run preliminary trials at your own computer, and you can fully see how the testbed is architected and how your software can fit into the testbed. We also want industry to use the testbed, for example, to certify commercial systems that do these complicated distributed controls. So what does the user have to do? So first, you need to obtain funding. And so if you're academic, then we could, for example, help you in writing your proposal to budget for using the testbed. Then we have a very simple application system, and then would accept you for the tests. Before we can do the real test, we would first go through a software test to see if the algorithm actually is robust and will not break the testbed. Then we do a hardware in the loop or real-time simulator test to make it more real life, and then finally execute the real test on the actual testbed. At the end, you'll receive all the data from the test back to you for analysis. Let me show you one example of how this test could be used, and that was for us a preliminary use of our campus testbed to show that we can actually do this. So in this case, we were trying to track a frequency signal that's here on the bottom. It's 40 minutes time series of frequency control. And we had these devices here on our testbed, so electric vehicles, storage, and the solar power systems. And then we executed a optimization problem where we had a cost function that was to be minimized, which is basically the sum of all the individual cost function of the individual DERs. And that sum then has to be following some power reference signal. And then each node had certain constraints and how high or low it could track the load. So we use different distributed controls methods like ratio consensus, primal dueling methods, and others. And then try to see how that worked out on this testbed. Here we had a distributed ring architecture for communications. So we had 9 nodes that were communicating just with the neighbors. And then each node had access to a certain amount of DERs. So node 7, for example, controlled the V2G, so vehicle to grid electric vehicle charging stations, and it was connected through an API server, so we could command these DERs. Same for several of the other nodes here. So here's an example of how well we were able to follow a signal. So here I'm showing on the top the air handling units. So those are fans and buildings. It's a 40-minute time series. This is our first test. This is our second test that we did. And it's the blue line is what we had asked the air handling units to do. The red line is the measured signal. So you can see these devices are more difficult to control. So we have larger deviations in this case. It improved somewhat in the second test, and we were better able to characterize these devices. Another example is electric vehicles. Again, test 1, test 2. And here you see we can track much better because here we're just really controlling the power electronics here, but still in this case, for the first test, we had some issues with the meter of the electric vehicle charging station. That was corrected, and then we were able to better track it in the second test. All right, so let me go over some technical details now of some of the components of the testbed. So some researchers may just want to use our buildings testbed, or others may just want to use our electric vehicle testbed, for example. So these components may be of interest to some of you. So for buildings, we have pioneered what's called the brick operating system, which is a way to interface with building controls without having to understand the full architecture of the building energy management system. In that way, basically this operating system can be used by different applications that you would write or you would augment. And you would not have to understand in detail how the building actually functions there. So application examples are, for example, social science tests where we have a digital thermostat where the user of the building could see on their screen what the temperature and the energy usage is that's associated with their room. And then you could, for example, request them to rate how warm they feel and then control the temperature accordingly, so we can see what mix of temperatures in different rooms in the building will best satisfy user comfort needs, but also reduce energy usage. Similar applications are there for building lighting, so you can change light levels. And electric vehicles, of course, you can charge them quickly, or you can charge them flexibly, and then in that way save energy and save money. So in the social science tests, we have this type of a framework where we first try to observe, and meaning that we recruit the users, we document how the operation works without interventions. Then we learn. So in the charging example, we can see how people are willing to pay more for immediate charging versus save money if they do flexible charging, and optimize the system, so meaning we optimize the incentives, and that way we optimize the behavior and the energy usage. So in the buildings example, we have a total of 12 buildings with over 1 million square feet of space. These are office buildings, one library, and we can see that here, and lecture halls. And then we have these DRs in those buildings. So we have the air handlers, we have a lot of light fixtures that we can control individually. We have plug load controllers that control printers and so on. Then we have sensors that will measure CO2 occupancy and humidity. That example is the DERMS system. So that's the Distributed Energy Resource Management System. This basically is the software that interfaces all of the different components of the testbed. So here we have the DERs. Here we have this hardware testbed in the lab. And then we have grid simulators. Now we can use this DERMS to read all the data and then issue control signals to the different components of the testbed. So here is one example of how we would do that. In this test, say we would have a distribution feeder that we want to simulate. So we input that feeder into our real-time simulator. Then we have the real DERs, so we can then locate these DERs on this feeder in a virtual way. And now the architecture of communications, we can configure that. So we may have 1,000 real DERs that are connected in a certain architecture. And then we can now simulate and as well as use real control to control these DERs to act in the right way on this simulated distribution feeder here to, say, track an HEC signal. Another example that we have implemented is plug load control. So here we have instrumented buildings with over 1,000 plug load controllers. So for example, here you see a water cooler. And so we can now, with this device, remotely control each plug load. So we can, for example, if a printer is not used, we can turn it off and we can shed load there. Here you see how much load we can potentially shed over a day compared to if plug loads were always on in the building. Thank you very much.
Okay, thank you, Jen, for the very nice overview of this testbed. Any questions from the audience? Yeah, Norman, go ahead.
I really like the talk, and I mean, having real buildings and loads participate in this testbed like makes it very useful and interesting. But at the same time, it may raise like questions: how would the actual users that are using these buildings would experience these tests? So do you have any comments on that? How did you envision that part of the system?
Right. Yeah. So that's indeed a critical question, because we want to maintain this testbed for many years, and so if the users are not cooperating, then we will not be able to do that. So yeah. So there's two answers here. One is we can run tests during unoccupied conditions, and that means that say at midnight or 2 a.m. even a university building is empty, and so we can run the test there, and that's where our sensors can tell us when the building is unoccupied or when certain floors are unoccupied. And the other is that if we actually do run experiments with real users, then we have to do all the work of notifying them, informing them, getting their consent to participate. So there's certainly ways for users to opt out of this experiment if they want to.
Okay, thank you.
Okay, George.
Yeah, this is a really interesting talk. I really enjoyed it. So I guess one question I had is, you've got the simulator component, you've got the microgrid component, there's a lot going on here. Is there any plans to sort of connect this with either the California grid or San Diego County more broadly, or, in other words, part of the theme of this workshop is connecting with society in different ways. And I'm just kind of curious what connections to the sort of San Diego City, county, state of California are potentially planned.
Right. Yeah. So we don't expect to operate this continuously, because that's a whole different ballgame, right? To operate a system 24/7. But certain aspects we could operate continuously. And what's a nice element there, actually, we already have a contract with the California ISO, so all of the California grid, through what's called the DRAM, which is the demand response auction market. And so actually we can bid currently our battery system, which is a large battery, into that market. And so, for example, in fall 2020, when the prices were very high because we had too much energy use on a hot day, there we could actually make money by using that battery. So in that sense, the framework is there. So we could actually take those, say, 12 buildings and electric vehicles, and also bid them into that market, either just during the very bad days of the year, or say if some buildings or departments actually want to participate every day, then we could enable them to do that too.
Okay. Any other questions? Well, if not, I have one last maybe simple question. You mentioned you have the 1 million simulate the DER. I was curious, how do you simulate this DER? I'm asking because sometimes if the DER is a kind of load, for instance, then you actually need to actually consume the power you actually deliver to these DER devices. So I'm just curious, how do you actually simulate that part?
Yeah, thank you. So that's a very good question, which is often a source of confusion for people. So we're not actually doing an electrically correct testbed, which means we're not trying to maintain, say, constraints of power lines or constraints of different loads. So for these simulated DRs, those are truly simulated, meaning they don't consume any real power, and in that sense, they also have no real effect on the frequency, of course, as a result. So in that sense, the reason why we do that is actually the actual frequency control really requires a lot more power than even what we have here. So it's not really feasible for us to engage in true local frequency control. So that's why some aspects will remain simulated.
Okay, great. Okay, thank you, Jen, for the very nice talk. I enjoyed it. So that will be end of the second session.